When it comes to simple GPIO-based peripherals, such as the button and the LED, we have a lot more flexibility compared to fixed-function peripherals like CAN or UART. Unlike communication peripherals, GPIOs are not tied to a single specific pin. As long as a pin is available and not already reserved for another critical function, almost any GPIO pin on any port, PA, PB, or PC, can be used for a button or an LED. From a hardware perspective, this gives us freedom. We can choose pins based on routing convenience, board layout, or which pins are already being exposed on a header. There's no strict requirement that forces us to use a specific port for these simple peripherals. However, this flexibility on the hardware side means that we must be very explicit in firmware. When writing code for the STM32, we need to clearly specify which GPIO port and which pin number the button and LED are connected to. For example, it's not enough to say, "This is an LED pin" in code. We must tell the MCU that the LED is connected to, say, GPIO port B, pin 5, configure that pin as an output, and then drive it accordingly. The same applies to the button. We need to configure the chosen pin as an input, enable the correct pull-up or pull-down configuration, and decide whether it's read using polling or an interrupt. This tight relationship between the schematic and the firmware is why pin selection must be documented clearly. If the schematic says the LED is on PC13, but the firmware assumes it's on PA5, nothing will work, even though the hardware itself is perfectly fine. So while GPIO peripherals give us a lot of freedom during hardware design, they also require discipline. Every choice we make in the schematic must be mirrored correctly in the firmware configuration. This is also why development boards often label GPIO pins very clearly, so there's no ambiguity when moving between the schematic, the PCB, and the code.